Good afternoon, and thank you for joining today's webinar from Spec Innovations, Developing Digital Twins. My name is Elizabeth Steiner, and I will be the moderator for today's webinar. Let's go over some quick housekeeping and introductions before we get started. So first off, your host will be covering the following topics: what is digital engineering, what is a digital twin, and developing digital twins in Innoslate. And for those of you who may not be aware, Spec Innovations provides systems engineering services and solutions to the aerospace, defense, and intelligence communities. Our flagship software, Innoslate, provides users with an all-in-one systems engineering software solution with requirements management, analytics, modeling, simulation, and analysis of alternative tools. We help organizations securely collaborate on critical projects throughout the product or systems lifecycle. During the presentation, feel free to send us questions during the panel on the right, and we will get them answered in the question and answer part of the webinar. The webinar is being recorded, and we will make it available to you after the live presentation, so be sure to keep an eye out for it in your inbox. Now I would like to introduce you to our presenter, Michael Campbell. He's one of our senior systems engineers here at Spec Innovations. He has a certificate in Manager of Innovation from International Association of Innovation. He is a veteran of the U.S. Navy, and he has a master's in systems engineering from Georgia Tech. And now I'll hand over the controls to Michael, and we will get started.
Well, good afternoon, everybody. Thank you for joining us. Seems there's quite a bit of you on here, so that's a good thing. So today we're going to be talking about digital twin and digital engineering and how we do that within Innoslate. So first we need to understand what is digital engineering. And so based on the system engineering body of knowledge, we have that the crux of digital engineering is the creation of computer readable models to represent all aspects of the system and to support all activities for the design, development, manufacture, and operation of the system throughout its life cycle. But ultimately, the goal of the digital engineering thread is to develop digital twins. And what digital twins typically are is a high fidelity model of the system, which can be used to emulate the actual system. And an organization would be able to use the digital twin to analyze design changes prior to incorporating them into the actual system. What this really does is saves a lot of cost and a lot of time when you can utilize the modular oriented system architecture, or MOSA, in order to swap in and out different products in order to test them synthetically versus actually having to purchase the equipment. So digital twins, what are they and how do they work? So essentially with digital twins, we have basically the physical architecture or the physical piece of equipment, and they are essentially identical, and that's why they're, they typically call digital twins. And so we have in tools, we use the data and the modeling aspects to create that digital twin with some embedded software in order to create a physical aspect of what we're trying to design. And then with some embedded software, we can also go back and forth between the two so that they emulate each other, not only in this synthetic world, but also in the realistic world. And that's essentially how we're working with the digital thread in order to develop a digital twin of the physical model that we're trying to build. So essentially what we've got in our tool is how we are going to build it in the real world as we acquire the parts and the parts of the model that we need in order to create that physical architecture and create the physical model, so we can then test the physical model as it works or as it looks, as opposed to the actual synthetic model that we use within the tools that we use to create that synthetic atmosphere. So, and the embedded software typically tends to be these kinds of software that we use for mathematical analytics and testing, modeling, 3D computer-aided models or computer-aided drawing, documents management, and doing overall analysis, utilizing artificial intelligence, and also providing simulation. And this is all to extrapolate data to determine that what we can do, at least in the synthetic world, we can also do in the physical world as we go into testing the physical system based off of the digital architecture that we've been able to provide. So essentially, like I said, we're going back and forth between what we're doing synthetically versus what we have as part of the reality, and they're basically going to be a mirror image, but one is just in the tool or on the digital environment, while another one is actually a physical environment with, you know, real parts and different types of materials that are brought in to build the system physically. So the benefits of digital twins is that we can visualize the system in real time, and that allows us to, you know, it's not going to take shape, but at least we understand what each part or each part of the architecture is going to look like, and we can do that with importing pictures into tools and at least getting an idea of what those items are going to look like, so we can eventually shape the design of the physical specimen or physical piece of equipment that we're going to build. This does allow us to make effective decisions quickly because there's not a lot of you know, labor-intensive time spent on creating or, you know, doing trade studies, because that's already been done. And that particularly allows the trade space to be a little bit more narrow, and so we can focus in on making those types of decisions quickly based on the type of performance parameters and the type of equipment that we're typically using to build the physical twin, which we've already designed as part of the digital twin. This allows us to also provide the traceability in a complex systems of systems, especially when you're dealing with highly complex systems of systems. This provides a singular way to test a system based on the replacement of a single part within the synthetic realm versus having to acquire multiple parts to test in the physical realm of the physical twin, as it relates to what the model I just showed you prior to this. We can also predict necessary maintenance as we test things and as we, the architecture and the physical model itself. We can also look at the documentation in order to understand the limitations of when maintenance is needed, when preventive maintenance is needed, or when unscheduled maintenance needs to happen. And that allows us to identify through user guides and data sheets of what kind of maintenance that is likely on the horizon, but also what kind of maintenance needs to be done in order to revive the machine, revive the physical product back to its normal state of operation. We can also troubleshoot issues from geographically dispersed areas. Again, if we're having, if we have a digital version of this, we can ultimately look at the digital version as we might be in a very dispersed area or a very you know, wide open area, which doesn't have a lot of technically sound equipment to get things out or to specifically tune into items. So we can take you know, information that we can utilize as part of what's happening in real time and troubleshoot from you know, all around the world, basically, as it relates to utilizing tools that can interconnect with the internet and cellular technology as well, in order to provide that information and be able to troubleshoot in real time. We can also test in the digital environment rather than the physical, and I've said this a couple of times, but that reduces the amount of cost and risk because we can do it all digitally, which doesn't take a lot of time to replace one piece of architecture in the physical architecture of a tool with something different that has all of the data already provided, and that essentially we can then run the simulations to test that information on the synthetic level before any acquisition of a physical piece of equipment, because that can typically get really costly, and if it doesn't work or doesn't integrate, that essentially increases your risk of not overall performance of the physical model, but also your cost allocation as well as your schedules. And then you can update analytics in real time to all stakeholders and allow in-field operators to adjust the system's assets when needed. So again, having the digital twin can certainly provide a global reach for all stakeholders involved in any project, so long as the proper pieces are in place in order to provide that information that's needed. So what role does model-based system engineering, or MBSE, play in digital twins? Well, these models would have to be connected to the physics-based models used by other engineering disciplines, such as mechanical or electrical engineering, as just examples, but there are other physical engineering disciplines that could also be involved in this as well. And those include areas of modeling, simulation, verification and validation, requirements management, architecture development, also functional modeling, behavior modeling, design and synthetic design, just to name a few areas that could be helpful as it comes for model-based system engineering, creating the digital twin environment to resemble its exact physical twin. So again, it's just these are very good areas of where it does happen, but there are other areas in which it can happen. And of course, one of the biggest things that's critical to just about any system engineering or model-based system engineering project or program, as we're developing products for the market or for the marketplace, and as we're doing our trade studies and technological reviews and requirements reviews, one of the things that we typically tend to need that we don't necessarily want to be worried about is an ontology. And ontologies are needed for digital twins to be synchronous with each other, and basically that becomes the challenge remaining for digital engineering is the integration of model-based system engineering with the physics-based models, like I said on the previous slide. So the foundation to digital engineering is the representation of the system data in a format shareable between all stakeholders, and this basically means a digital format. It's a way to get information to all those stakeholders through a single view, without having to basically send emails back and forth, and having to risk the potential loss of data based on shipping files between different types of file transfer systems like SharePoint, et cetera. If you're able to do it within a tool and have the tool be part of that database for the building of the product that you're trying to get to, it's best if you're able to do it in an environment like that. SysML 2.0 is one of the several future developments which is promising to provide a representation sufficient to support digital engineering. An ontology defining the entities and relationships between them can be used to define the concepts relevant to systems engineering. Now, SysML 1.0 wasn't quite the ontology of what a true ontology should be. There was a lot of flexibility in digital engineering, or I'm sorry, in SysML 1.0 up to whatever number they reached. I think it was 1.6, 1.7. And there then became a need to rethink SysML 2.0 and understand that things needed to be a little bit tighter as it came to their models or the SysML models, and understanding what a true ontology really is meant for. So it takes a true ontology takes a lot of the guessing game out of what each person who is working within a team is trying to get after, with different naming conventions, relationship types, and understanding how to effectively model in a synchronous way with the other members of your team. And so this is where having a stringent ontology is very important. And so, such a representation is necessary to create the digital thread linking all models together in a cohesive and useful manner. So that's brought to you through the system engineering body of knowledge. But the beauty of this is that lifecycle modeling language, or LML, is there. It's been there for the last 6, 7, 8, 9 years that it's been out, since the first instance of it of 1.0. So if you haven't checked it out before, you should check out the Lifecycle modeling language. It's fairly easy to use, and it's a lot more practical in terms of the use of a modeling language for systems engineering that focuses specifically on systems. So just a quick background about it. Lifecycle modeling language, or LML, was developed by a group of systems engineers who realized that SysML was not meeting the needs of the system engineering community and program management communities. The group was led by Dr. Warren Vanneman, who is a Navy captain, retired, who also is a professor of practice at the Naval Postgraduate School in Monterey, California. And lifecycle modeling language is taught in over 200 universities around the world, including MIT, George Mason University, Stevens Institute of Technology, West Point, Naval Postgraduate School, Air Force Academy, and obviously many others based on the 200 number. Frankly, it's easy to learn, it's easy to use, and it is extendable. We have a schema editor in Innoslate that allows you to be able to extend the LML schema in order to capture the information that you're trying to represent. And the picture is very telling about what is needed for LML versus what SysML provides. Essentially, SysML requires the practical guide, which is nearly 800 pages long, and then the distilled version, which is just over 200, so 900 pages of how to explain SysML and modeling languages within SysML. But Essential LML, that book is about 60 pages long, and it uses natural language properties in order to be able to utilize modeling and how the modeling connects with each other, with each of the models based on the relationships. And that's really what it comes down to, is understanding how to utilize the relationships within the connections to model effectively, instead of having to determine what other people are trying to model based on a completely different terminology. So LML has proven to provide a strong ontology for the system engineering and program management disciplines as they relate to today's modeling environment. So how do you develop digital twins in Innoslate? So Innoslate integrates system engineering activities across the entire life cycle. So we're all familiar with the systems engineering V, from concept and operations all the way to demolition and disposal. And it's not completely linear. It is something that we do across the V as well as down the V. And then program management does, kind of overshadow all of these areas of the V. So Innoslate does have a documentation view or documents view, in which basically you can create any document, upload any template you want, modify a template to create a custom template, or use one of the templates that are already provided. And we have, I believe, 11 different templates as part of the documentation. And we're always looking for more of ones that are standards that are across, different areas of use, such as DoD, DOE, etc. So if there are ones that you think would be of use, we could certainly look into that. But we do have concept operations, test plans, requirements documentation, notes documents, IV&V type documents, and many more. You can create many documents through this view in order to start the part of the concept as you're starting your project out. Then comes requirements view. So again, like I said, requirements view is somewhat like documents view, in which you can, but they basically, any type of document that you import into the tool is going to be drawn into the requirements view, so you can do analysis. And that's essentially what we're anticipating, is that you get requirements first of what the system should do, and that way you can analyze the requirements, and this will help drive the functionality and the actual functional modeling of the system to meet the customer or stakeholder needs. And we also have, like I said, we lead into the functional modeling, but that functional modeling is going to set up the actual physical modeling as well. So any of your physical architecture, because as an action is performed or a function is performed, something has to perform that action. And that's where the physical architecture comes into play. We do have a CAD viewer that's built into the tool. So if we have, you know, an OBJ or an STP file, I believe they are, they will upload and you will be able to see the actual view of the model that was developed within a CAD viewer. And you can also bring those assets into the database as part of the CAD viewer. So as you're coming across the V, ideally we're setting up test plans, which again goes back to documents view, and creating those test plans as we're creating the functional models, so that way we can test the physical model once it's been you know, acquired, and we've looked at the parameters and the performance, and we've met all of the requirements, at least synthetically, on the left-hand side of the V. But on the right-hand side, the simulation part will help to determine if we are in the right area for performance, also along with cost and schedule, and just making sure that, you know, the program is on track to be you know, developed as part of what the agreed upon schedule is. And then we do have Test Center. Test Center is what we use to create our test cases, and these test cases are what's going to help define or help test or stress the system, the physical system, to ensure that it will perform to the extent of what we have as part of the modeling and simulation environment within the tool. So this is a great way to be able to connect all of these types of linkages here with the different relationships that we have in the tool and as part of the strict ontology that LML is. So we can connect our test center or test cases back to verification requirements, and also to the verification methods, and that will also trace back to the original requirements to show not only the level of traceability, but also to show the completeness of integrity or, you know, fidelity as it relates to the modeling of the system and actually testing the physical parts of the system to ensure that, you know, you've got it right from one side to the other of the V. And that's ultimately what digital twin is meant to do, is on the left-hand side as we simulate or as we model and simulate, on the right-hand side as we build the tool, that the items that we have as part of the physical architecture are meeting or performing to the extent of what the physical architecture is doing. And we always want to do risk analysis. It's a constant thing that's ongoing. As programs or projects develop, new risks always pop up. The biggest things to always be aware of are cost, schedule, and performance, to ensure that, you know, you're meeting stakeholder needs within budget and on time, and within performance. And again, Innoslate carries that with the risk model or the risk table here that's shown, as well as using actions and issues and things, those types of classes, in order to demonstrate how to mitigate the risks as it pertains to the project, in order to reduce the probability of those risks occurring. And to help with the scheduling, to identify pertinent milestones or deliverables when they're due, progress of specific actions or items that are coming up. We have the timeline diagram, which is meant to kind of look like the DoD acquisition diagram, with the milestones up top in diamond form, and then the triangles that connect or that show the progress of an action being completed based on its deliverable timeline. And we can show that through that diagram, which also can generate to an action diagram, and then we can then simulate that to see where where our timeline lies based on the deliverables that are needed, and to ensure that we're staying on schedule. And that can be done weekly, can be done daily, could be done hourly. It just depends on, you know, how often you want to be able to do that. But again, if we're talking digital twins here, we want to make sure that we're staying on time, and making sure that that we're actually progressing from simulation, modeling simulation over to the testing and building the physical product in a timely manner to give enough time for that testing. So this is where the timeline comes in handy to ensure that you are meeting those timeline types of requirements or deadlines. And then we can also use hierarchy charts to break down the work breakdown structure. And again, these are actions that are going to, basically define what needs to be done as part of the building of the system, not only from the synthetic side, but also from the physical side. So there are going to be items much like systems engineering and program management and operations and cost schedules and things like that, that all need to be defined as part of the work breakdown structure and then assigned to those areas within your program to help deliver the information as part of that model. So Innoslate's digital twin software integration approach. So basically, if we're looking at the V again, Innoslate does provide a complete model-based system engineering environment. I don't think there's any question about that, that we do cover, current operations and maintenance or concept definition or even, little seeds of ideas to all the way down, to developing the product and all the way and bringing it all the way to, some level of either demolition or new iteration. So Innoslate does provide that complete end-to-end full lifecycle environment. But we have added integration with MATLAB, the Satellite Toolkit, and GitHub in version 4.4, which was just released a little while ago. I don't know the exact date. We've also got a Java web application, which is used to interface between the Innoslate Cloud native tool and desktop tools. So again, that allows us to interface with MATLAB or the SDK or different areas that require those types of web applications, ANSYS as well. And we are in the process of integrating with the ANSYS tool suite, LabVIEW, and Selenium to complete the digital thread software. So again, these are other different, software tools that allows us to integrate with instead of having to build with it. And we're basically improving the entire system engineering environment through integration and development of all of these tools instead of having to do it all at once and trying to take away from others that, from those that have already done this. And that's it's a benefit for not only the system engineering environment, but also for the tool environment as well, because it provides that standard or that basis for creating the digital thread within your system engineering program. And then if you look at what just popped up on the screen here is the orange box, and this was what was already implemented in 4.4. So like you can see, Selenium, LabVIEW, and ANSYS, the ANSYS tool suite, as well as HoloLens and voice transition will all be implemented at later dates. So our integration is enabled using the MOSA architecture or Innoslate's MOSA architecture. And so again, it's modular open systems approach architecture. And so what we've done is we've used plugins, which are viewpoints of the Innoslate database. So in this case, we have the MDEE ONS plugin and the Innoslate plugin, which connect or utilize the REST APIs. And the plugin features it's not a standalone application. It does require Innoslate core, which is basically what you're seeing here. And all authentication is through Innoslate core with the options for single sign-on, such as CAC or a CAC authentication, native email or password, and LDAP, which it's another form of authentication as part of security measures to ensure that your data is meant to be secure. And then all data is stored in the U.S. government managed MSSQL database using the Innoslate core, and there is no data lock. So MS SQL is Microsoft SQL, but so it doesn't completely lock up your data, and it will only show when you log in with your either CAC or native email password, or if you have LDAP enabled. And Innoslate REST APIs facilitate the plugin data exchange, so that allows the data to move back and forth between the SQL Server, the Innoslate core, and the REST APIs into the plugins to allow the integration of the MOSA architecture throughout. So we can plug and play basically as it comes to putting in new tools and new integrations and making sure that we can cover that digital thread environment. So we've got documents view here. It's kind of like what I mentioned earlier. It does enable you to capture and develop your documentation. It provides a means to capture pictures, create tables, use the diagrams and charts from Innoslate and create live tables. You also have live documents, or I'm sorry, live diagrams, in which if you change it in the actual diagram and it's represented here in the document, then it will change in the document as well. That way you don't have to go changing a diagram in 14 different places. It'll automatically change in this particular area. You can develop your own custom template. Like I said, you can use these documents to perform model-based reviews. And the biggest benefit is that you can show users and customers information in a simple form they can easily understand, yet be reusable and traceable to other parts of the design. These can also be generated as a report as part of a deliverable in order to hand in hard copies if need be. But this does also allow for the stakeholders and interested parties to be able to view the document in real time to see, where the project is and what's actually happening. And these can be baselined as well. These can also be, you can have multiple versions of these. So it's a very useful and extremely useful way to capture your data and be able to present it in a meaningful manner. Requirements view, a little bit different than documents view, but still kind of acts the same. There is a hierarchy here. What you're seeing on the picture is a verification requirements document, but we can identify our rationale for the requirement. We can show our quality score, which is unique to Innoslate. It's the only tool out there that actually does an analysis or initial analysis of your requirements and how good they are. You can identify or place labels on each one of these items in order to sort and to categorize items into a specific area. And much like a file folder system, typically you only have a single area for file folders, but in this case you can categorize it into multiple areas, and that's why we went with labels as opposed to working with any file folder method. So like I said, it's a special type of document. It includes by default the rationale field, quality score, and quality checker. It can also see indicators for key traceability relationships. So again, if you see on the table there, the small green letters that are T as in Tango, V as in Victor, and S as in Sierra, those simply mean that that item or that entity has been satisfied, traced, or verified. And those are just visual indicators that lets the user or the stakeholders know that the relationship has been defined. This view has all the benefits of any document and documents view, including baselining, formatting, acronym extraction, find and replace, and a whole heck of a lot more. The search feature is actually quite elegant, so to speak. This also uses workflow to manage requirements, so you can set up a workflow within the tool to help manage requirements as they move through an approval process. Again, using labels for sorting, and then the benefit is a digital document for your living requirements. Requirements are constantly changing, so this will specifically help for the capture of requirements, baselining, and then seeing how requirements change over time. So we've got multiple modeling views. I mean, I think we're at 29 different models now, but we can create high-level to detailed models of functional and physical elements of the design. The functional model or the action diagram or a behavior diagram, if you're familiar with, provides means to allocate the decision points and use resources explicitly. And that's you can see it's labeled with the functional modeling up top. In this case, we can also allocate actions to assets. And like I mentioned before, assets perform actions as part of the ontology relationship. And basically you can automatically allocate the action to an asset, which is functional to physical mapping. You can also view or use models in many different formats, including SysML, I0, etc. I mean, there's many diagrams. And we can reuse portions of the models in other models, including across Innoslate projects. And the benefit of this is to develop the functional requirements and physical constraints. And this allows us to determine what's best going to suit the physical architecture and the build of the product. And then we can use simulation as we gather data and as we capture data within the tool, we can then provide simulation as part of the functionality. And again, we're looking for performance, but also cost and schedule as it pertains to the actual program. But we are looking for performance and ensuring that we can meet deadlines and that we can also meet the performance or KPPs or KSAs of a particular product that we're trying to develop for a customer. So Innoslate does provide built-in discrete event and Monte Carlo simulators. There are decision points that come with pre-built scripts, which are JavaScript for probability and resource selection, as well as iterations for loops. And that's one of the constructs in the action diagram. JavaScript can also be used to enhance the simulation execution. It can also provide, kind of a customization of the simulation for a little more randomness, a little more unpredictability as far as decision points. So you can generate, you don't automatically know that it's always going to be 80-20 or 60-40. It can be a random distribution of different pathways. So that way it becomes less predictable, but more random, so you can generate an idea of how things are going to operate. You can access web resources using the APIs. You can also access the integration with MATLAB and Simulink and SDK through the special APIs. And major enhancements are coming to the simulators in development for version 4.5. This is the current version in 4.4. And we have the white or dark views, which are really nice for presentation purposes and identifying just the different data points that need to be represented. And the benefit of this is to derive performance requirements for timeliness and quantity using distributions and resources. This is one of the best benefits I've ever had with a simulator and utilizing that for data extraction from models. And then we can use all of these models for analysis. So Innoslate does support various types. So we're talking textual analysis using NLP or natural language processing algorithms, requirements, quality analysis, dynamic analysis, static analysis, risk and cost analysis. And then we can also use integration with other tools, like I said, with MathWorks, MATLAB and Simulink, ANSYS, AGI systems toolkits, and more. And you can see here we've got multiple diagrams: physical I/O, traceability matrix, the intelligence view. We do have now the new interface diagram, and then we also have the risk burn down chart that have all been implemented prior to 4.4. So you can do mathematical analytics with MATLAB. So again, it's creating a unique rover function script, and it shows under the simulation settings, you can actually have the integration URL. You input the integration URL as part of your model, and that and when you submit the script as you run the model, it will run through the integration of MATLAB to get you the detailed calculations, and they're simple get and post commands, which move data between Innoslate and MATLAB. And then you use the setting to show the pathway. And again, the benefit is to reuse models created in MATLAB to perform more detailed calculations. And that really gets you into a lot of the calculations that you can possibly need as part of an engineering effort. Okay. Oops. All right. Geospatial visualization and analysis with STK. STK is something that's been on the horizon for quite a few different developers as of within the last 5 years or so. It's a very useful tool, and being able to integrate Innoslate with an SDK allows us to kind of explore the other areas outside of our own world that we can see, and we can actually start modeling satellite tracks and things like that. So the SDK integration is used to visualize and take advantage of the SDK analysis tools, such like what we're seeing here. APIs are designed to get the critical parameters in the SDK, and then we use the information to alter the simulation performance in co-simulation. And the benefit is that it includes geospatial constraints in the discrete event simulation for more realistic analyses. And you can see, kind of the scripts that are provided into these, and we just add them into the action that's doing this, and it will basically call for those APIs and perform the script or execute the script and provide that detailed information as it pertains to the action that's being performed. So again, utilizing an SDK integration is very helpful as we're talking about developing search patterns or communication satellites, or with communication satellites. So the computer-aided design or computer-aided model, actually it's drawing, Innoslate does have the CAD viewer, which allows us to import a CAD file, which can then provide the image, much of what you see here. So in this case, we've got the Curiosity rover, looks like a hypercar of some sort, and then the International Space Station or some type of satellite as part of the OBJ files or a potential zip file. And then they've also got a GLB file up there, and I think there's one other, which is now actually, yeah, so added other file types such as GLB, GITF, 3DS, PLY, and zip with OBJ and MTL combined. So the benefits of this really is to enable verification of the design and links back to the requirements. Again, synthetically, you can see what you're building based on the CAD model. And it all becomes part of that digital twin to ensure that what you're building here looks exactly like what you're building outside of the tool, based on the information that you've modeled prior to this information. And then we can do software development integration. So we do have a new GitHub view, which provides capability to directly interface with GitHub using a special set of dashboards. We can provide an entire new viewpoint to enable program managers and systems engineers to more effectively monitor software development progress and capture results. Version 4.5 will include capability to create class diagrams from code to enhance traceability between the requirements in code. And then the benefit of this really is, again, it's being able to just integrate with a bunch of different views, but that the capability to monitor software development progress and verify code that meets requirements, as part of an overall program as code is being written. Usually that always happens during acquisition, or at least, as we're going into integration, some code needs to be written in order for different products to be integrated with. So this is a great way to be able to identify those areas and make sure that the information is actually being developed and it's meeting the requirements that are expected for the performance of the product. So augmented reality and virtual reality. Innoslate is a browser-based, making it easy to use with augmented reality or virtual reality technologies such as HoloLens. It's useful when field operatives need to be able to view the digital information, such as standard operating procedural diagrams, test plans, or metrics. And the benefit is that you can, basically you have enhanced visualization of design elements during operations. And this, again, it's utilizing modern technology to be able to capture information and view different things when you're not sitting on a computer. So you can actually go out to, in the field and capture information and have that be sent back via cellular satellite technologies in order to provide the information back to home base and allow home base to capture that as well and implement it into the data or into the model. Operation support. So coming soon is a tool called Sopatra, which is powered by Innoslate. Basically, this is a text-to-diagram auto-generation used to transform written standard operating procedures, or SOPs, to action diagrams for analysis. And it uses advanced natural language processing algorithms, which have been developed, and it automatically adds best practice actions such as see and decide. It does provide a special Monte Carlo analysis of the allowable operational time window, or AOTW, and time of procedure, or TOP. This also provides advanced analytics to calculate the procedure buffer time. And the biggest benefit is to provide more accurate standard operating procedures, or SOPs. So look for that in the near future as it's being developed. So if you want to get started with your digital twins, create an Innoslate account at cloud.innoslate.com/sign-up. Or you can just go to innoslate.com and there's a sign up button up on the upper right, and that can get you the free account. If you do need to utilize our resources, we have help.innoslate.com or innoslate.com/resources. And if you do need help with anything, we do have a support team that works on any issues users might be running into, and so you can utilize the innoslate.com/contact us to access that capability. So I believe we have a little bit of time for some questions and answers.
Hi, Mike. Thank you so much for that. We have a few questions already. Our first question is, can you tie 3D model objects to Innoslate objects?
So with 3D model objects, as they're brought into the CAD viewer, they do create, you can create assets from those 3D model objects as items or entities within the database. So yes, you can connect those into other entities within the database, yes.
Is the modeling done on the platform or in 3D modeling software or CAD software?
Right. So if you're doing the 3D modeling, that's going to be done in computer-aided drawing or computer-aided modeling software of your choice, so long as the output can provide the file types that were mentioned in the slide. And that way you can just bring that into the tool, and we've got the viewer that will render it for the 3D model. But again, those can also be related to the entities within the database as part of your traceability.
Thanks, Mike. Our next question is DON Chief Data Office interested in providing Innoslate as part of the Jupyter tool suite?
I don't have the authority to make that decision. My guess would be yes, but I will have to ask my boss to ensure to make sure to see if that would be a route that they would want to go to, and of course there would be talks that need to happen in order for that to happen. So, but yeah, if you can leave your point of contact or your information, we can get back to you to see about setting up a meeting of that sort and talking with the bosses that make those decisions.
Thank you, Mike. Our next question is, similarly, is LML included in Innoslate? Are there plans to add it to the Naval Integrated Modeling Environment? Thanks.
So yes, LMLs, so Innoslate's primary modeling language is LML. The SysML that we talked about, or that at least I talked about as part of the original or the initial introduction to this, is that it is SysML, but it's been mapped to LML in order for the tool to be consistent across the board. Because, like I said, with some of SysML, it's very open-ended and loosely tied. So LML is very strictly tied as part of an ontology, and it doesn't deviate from that. Where you can utilize SysML to put multiple things on multiple diagrams. There's no actual real rules that happen with SysML diagrams per se. I mean, there are some rules, but they're just very loosely coupled to their diagrams, so it makes it difficult. But LML is the primary language for Innoslate. Again, for the the Navy question, you know, we definitely would love to see LML implemented in a lot of different areas. It's already being implemented in quite a few areas, but we definitely want to see it in multiple areas. So that's a question for the bosses, just to make sure that they can, you know, that it's something that they're interested in. I think they would be, but I don't make that decision. So I would certainly say that they could do that.
And then we have a question about if Innoslate Cloud can be used with Java web application to interface to external engineering tools such as MATLAB, LabVIEW, Simulink, or if you need to be using Innoslate Enterprise.
That's a very good question. I believe that Innoslate, because it's web-based, it can be, I think both are being designed for that reason, that purpose. So I think the cloud and enterprise are going to be usable, so long as the biggest question for enterprise really is, you know, if you've got the tool on a server, it's going to be hard to get the server to connect with something outside of your firewalls. And so that may or may not be something that's, you know, one of those hurdles that you might need to conquer in order to implement that. But, you know, we can certainly, you know, look to help with that kind of obstacle. As far as the cloud goes, I believe that we've already tested it on the cloud, and that's essentially where you're seeing a lot of this integration happening at the moment.
Our next question is, can you elaborate on the API capabilities? I'm a systems engineer, not a software.
Well, same here. So the API capabilities, basically they're the REST APIs. They use the call functions, but I don't get too much into the software area. So you know, basically APIs do allow you to integrate with a lot of different tools, which can, you know, basically you're calling data calls, or you're using data calls to bring in data from different areas in order to integrate with that tool. And so they communicate that way based on the API. I don't know much more than that, or getting into that type of information, but I do understand that APIs are kind of like a link to each other, in which you have if they share the API you know, key, then you're able to connect with that and provide that type of information exchange as needed.
Thanks, Mike. Our next question, with your industry experience, what's the best way or suggestions on how to best showcase Innoslate and its digital engineering capabilities? From my experience, I see Sparks EA, JAMA doors gaining more steam in industry than Innoslate.
Well, that's a good question. So if you're seeing those tools gaining any steam, it's only going to be in specific areas. So when you see a tool like JAMA, it's going to be requirements based. When you see a tool like Sparks, I don't think you're going to get the development or the enhancement functionality that you're going to see in Innoslate. The best way to showcase Innoslate is really by use and ease of use, and allowing not only your stakeholders being able to see how convenient and easy it is to develop the models that are needed, but also to integrate with other tools. That's the biggest thing that we have tried to implement with Innoslate over the last 10 years that we've had the tool out, is to ensure that we are being able to capture full life cycle, because a lot of these tools aren't full life cycle. And they may claim to be, but they're not actually providing full lifecycle implementation. They're not actually providing any type of development beyond what their capability is now. And as you can see that from this presentation, we're developing that. As technology improves, we're always going to be behind the curve as technology improves. We can't outrace technology. Technology is always improving. The best we can do is to take what is out there that we find is viable and develop to that based on what our discipline is asking for. So, you know, like the development of Geospatial, which is going to be text to model type stuff, utilizing augmented reality and virtual reality in order to provide that information. So that way you can send information or capture information, you know, without having to be completely connected to the internet and be reliant on the internet, where you can utilize those types of functionalities in order to stream the information back to home base or to field vehicles or whatever in order to capture it in real time without relying on having some type of digital connection. You could use cellular, you could use satellite, based on those areas. But the biggest thing that we can do right now is we can evaluate what technologies are important for the discipline to move forward as a whole and implement those. And hopefully, a lot of our stuff is developed based on customer and user input. So we typically tend to develop based on what are some of the biggest areas of interest based on user input. And so that usually is where it comes down to providing all of that information and developing as part of the tool.
Thank you, Mike. Our next question is, are you familiar with MOSA that integrates SDK with Cameo/SysML? How does Innoslate integration with SDK differ?
So I'm not familiar with MOSA. I am familiar with Cameo. I do know that Cameo is they're obviously the bigger plugins for for Magic Draw. How does it differ? Well, I don't think there's a huge cost in integrating Innoslate with an SDK, which we've already done, versus having Cameo do it. Where I think that's an extra cost on top of it as part of a plugin. I haven't played with MOSA, and I haven't actually looked at the integration capability through Cameo, so I'm not exactly sure, and I don't want to give you false information. So I think that, at least for our end, the integration with Innoslate and the SDK tool that we've got, which I want to say is AGI, but I'm not gonna bet my life on that. But it's fairly seamless, and we can, the image that you saw back on the slide was, from that data point. So, which is this slide here. So that's our SDK right there, with the integration based through the action diagram.
Thank you, Mike.
Sure.
Our next question, how do you handle configuration management wherein different users are making changes?
Well, the tool actually, so if you're doing collaboration within the tool will basically use it as first come first serve based on which items were saved, and so it syncs to that, and then anything done after that would have to be either be redone. Yeah, it would have to be redone, or if it was not meant to be there, meaning it was being developed as kind of a hypothetical, or the item was already developed by somebody else, or the entity was already created by somebody else, then you just move on. But in terms of configuration management and dealing with those types of items, really Innoslate relies on the ontology to perform at that level in order to ensure that we don't have overlapping information, nor do we have items that are going to be running into a conflict based on collaboration.
Thanks, Mike. Is it planned to integrate Mathematica, Maple, and Modelica into the next Innoslate version via special APIs?
Well, that's a good question again. I think the best answer for that is we would have to take a look at it. I don't believe that is those are some of the tools that we are looking at. I do know that we have been working with MATLAB just because it is one of the more popular ones, but it doesn't mean that we couldn't integrate with Mathematica or the other tools mentioned. It just depends on the type of API connection that we can make and what kind of information we can get from it to implement into the tool, and how difficult would that be, so to speak. So if you can give me an idea of who makes that software, if it's not by that name Mathematica, then we can certainly pose it to the developers and see what they think. But at the moment, based on the integration that we're trying to do with LabVIEW and HoloLens, and with the stuff that we're putting out right now, or that we've put out through 4.4 with MATLAB and STK and those types of software, I think some of those software are going to meet that need potentially, but it just really depends on what can the softwares that you named, what can those provide us that the other ones are not, so we can determine if the integration would be beneficial, not only for us, but for you as a user.
Thank you, Mike. That's all that we have time for today. If you have any questions after the webinar, please feel free to reach out and we'll be happy to help you. We would like to thank you again for joining us for today's webinar. Make sure to join us next time for our next webinar, MBSE Approach to Portfolio Management, on Tuesday, August 17th at 2 p.m. Eastern. As always, we will be sending the recording and slide deck to everyone that attended today. For more resources, we encourage you to visit our website and our blog, as well as connect with us on social media through the Innoslate users group or through Twitter using the handle @Innoslate. That concludes today's presentation. Thank you again for your attendance, and we hope to see you again at our next webinar. Please enjoy the rest of your day.